Hi everyone, this is Ms. Wong, and you're listening to the presentation on forces and force diagrams. If you haven't done so already, add to your table of contents in your journal the date, the title of these notes, forces and force diagrams, and the page that you're going to take notes on, and then turn to the next blank page so that you're ready to take notes. At any time during this presentation, you can pause the presentation so that you can finish taking the notes that you need to. All right, let's start with our definition of forces. Our formal definition is this: a force is a push or a pull upon an object resulting from the object's interaction with another object. Write this definition down in your journal. We can think of forces as things that cause objects to move, cause them to stay in place, or cause them to change their movement. And we can think of all forces or interactions between objects as being placed into two broad categories: contact forces and forces resulting from action at a distance. In our notes, we're going to write down the examples of contact forces and forces resulting from action at a distance, as well as their abbreviations. Go ahead and pause the slide now if you have not yet taken down the definition of a force. Let's write down this table in our notes, the types of contact forces and their abbreviations. We've seen each one of these in the Feel the Force lab, so I'm going to talk about them briefly here. We observed frictional force at the station with the whiteboard and the blocks. The block did not slide down the rough side of the whiteboard as easily as it slid down the white side of the whiteboard because the rough side of the whiteboard had more friction. So there's frictional force that was preventing the block from moving. We observed tension force in the station with the rubber bands and the weights. We called it at the time elastic force, but from here on we're going to call it tension force, which is the pull that was acting on the weight to keep the weight from falling to the table. So it was a tension force from the rubber band. We simulated normal force at the station with the books. So you were simulating a push up on the books that was counteracting the push down from gravity. So you were simulating what's called normal force, or the force that acts against gravity. We observed air resistance force in the station that had the paper. So when you dropped paper, you noticed that the paper that was open had more air resistance than the paper that was crumpled and therefore fell to the ground slower. Applied force, you applied force at the station with the ping pong ball in the water when you were pushing the ping pong ball under the water. So applied force is any force that's either a push or a pull that's a contact force. And then finally, buoyant force you observed again at the station with the ball and the water, which was the force of the water pushing up on the ping pong ball to cause it to float. Pause the slide here if you haven't yet finished taking down what are the contact forces and their abbreviations. Here's our list of at a distance forces. So again, write down this table and their abbreviations in your notes. Gravitational force, electrostatic force, and magnetic forces are all action at a distance forces, meaning that they don't require direct contact between the two objects in order for the objects to interact with each other. Gravitational force is at play with any object on Earth, so when we start to diagram forces, you're always going to include gravitational force. Electrostatic force we observed at the station with the balloons, so one balloon could cause another balloon to move because there's electrostatic force between the two balloons. And then magnetic force we observed at the station with the magnets and the paper clips. The paper clips were able to jump up and attach to the magnet because of magnetic force. Pause the video here if you need to take more time to write down your action at a distance forces. All right, we're going to move into how to draw a force diagram. So a lot of this unit we're going to be representing the interactions of forces as what we call force diagrams. So write down this information about how to draw a force diagram. Step 1, represent the object that you are talking about by a small circle, like what you see represented. Step 2 in drawing a force diagram, You're showing the direction that the force is going by an arrow that is pointing away from the object. Even if the force is acting directly on the object, for example, if you're pushing on the object, you would not draw your arrow pointing toward the circle. You would always draw your arrow pointing away from the circle. Step 3, the amount or strength of the force is shown by the length of the arrow. So a very strong force is shown by a long arrow, and a very weak force is shown by a short arrow. Step 4, you're going to label each arrow with, first of all, the type of force. So example, normal force, gravitational force, air resistance force, and you're going to use the abbreviations that you wrote down previously rather than writing out the force. And then each arrow is also going to have these words: the force acts on the object by another object. Pause the slide here if you need more time to write down how to draw force diagrams. All right, let's go through how to draw a force diagram with this example. So at this point you just have to listen, because we're going to draw some examples in our journal in just a minute. So step 1, the object is represented by a small circle. Let's say that we're looking at a dog that's sitting on the ground, and the dog is being pulled by a leash to the side. So we're going to represent that dog with a small circle. Then we're going to add arrows. That's steps 2 and 3, and the arrows represent the strength of the force that's acting on the dog, as well as the amount of force that's acting on the dog. Step 4, you're going to label the types of forces that are acting on the object. So in this case, the dog is being acted on by gravity, pulling the dog down to the earth; normal force, which is counteracting gravity; tension force, which is the force that is pulling the dog by the leash; and then finally friction force, which is counteracting the pull of the leash. Finally, step 5, you label each of those forces as on object by object. So for example, the normal force is acting on the dog by the ground; gravitational force is acting on the dog by earth, and we always say this for gravitational force, that gravitational force is acting on the object by the earth, because that object is being pulled to the center of the earth. The friction force is being acted on the dog by friction, and then the tension force is being acted on the dog by the leash. So the leash is causing the dog to be pulled, and that type of force is called tension force. So that's why we say that tension force is on the dog by the leash. Here's some example force diagrams of people that are at rest, meaning they're not moving. So if there's someone who's just standing on flat ground, you can see that gravity is acting on that person and normal force is acting on that person. That person's not moving, but they still have forces acting on them. The person on the ramp is also not moving, and gravity is acting on the person, normal force is acting on the person, and friction is also acting on the person. Friction is preventing the person from sliding down the ramp. So something to notice for these two diagrams is that for both of them, gravity always points straight down, and the force of gravity is always labeled as on the object by earth. So gravity always points straight down. Normal force, on the other hand, is dependent on the angle of the surface. So if someone is standing on flat ground, then normal force goes straight up, because normal force is perpendicular to the surface that that object is on. So notice that for the person on the ramp, normal force actually angles off to the left a little bit, because angling off to the left puts the arrow perpendicular to the slanted surface. Here's an important idea to write down in your journal. So the sum of forces on objects at rest always equals 0. Right now we're not going to associate any numbers with forces, but we can still represent the sum of forces, or the net force on an object, with our arrows. So we call the sum of forces the net force, and that's abbreviated as F net. So how do you know, using a force diagram, whether or not the net force is zero? Well, you have to consider the arrows. If you put the arrows so that the start of one arrow is at the end of the other arrow, and you end up back in the same spot, that means that the net force equals zero. So here's what you do. For the object on the left, you can see that when you put the two arrows side by side, you end up right back at the same place, so there's no unbalanced forces. Your net force is zero. For the diagram that's on the right, notice that we put the beginning of one arrow at the end of another arrow. So in other words, you put the pointy part of the arrow on the end of another arrow, and notice that you end up right back at the same spot. So again, this represents that the net force equals zero. Alright, so let's practice drawing a force diagram for this book at rest on a table. Go ahead and pause the slide until you have drawn a force diagram for this book, and then we'll check our answers. So your first step is that you should have represented the book as a small circle. And then for steps 2 and 3, you add on the arrows that are acting on the book. Then for step 4, you label the forces that are associated with each arrow. So this book has normal force that's pushing up on it, and gravity force that's pulling down on it. Then you write in what are the things that are acting on the book. So there's normal force on the book by the table. The table is pushing up on the book. And there's gravity force on the book by the earth. Let's do another example. Here's a dog on a ramp at rest. So write dog on a ramp at rest. You can do a little sketch if you'd like, but then also underneath, draw what you think is a force diagram for this dog. Pause the slide until you're ready to go on. So here's our force diagram. Again, notice that gravitational force goes straight down, and normal force is going off to the right, so perpendicular to the slanted surface. And then friction force is preventing the dog from sliding down the ramp. So if there was no friction, the dog would have slid down the ramp, but since there is friction, the dog is not sliding down the ramp. So friction force always points opposite the direction that they would be sliding. So can we see from this force diagram what the net force is? Sure, so we can remove the arrows. So we can take the arrows and put the end of one arrow on the point of the next arrow. And we do that for all 3 arrows. Notice that you end up back on the same spot, so that means that the net force equals 0. And this makes sense because the dog is at rest. Let's do one more example. So here's Miss Wong on a rope, and I'm at rest right now because I'm taking a break from rappelling down the rock. So pause the video and draw a force diagram for Miss Wong on the rope. Here's our force diagram. So again, gravitational force points straight down. There's normal force that's perpendicular to the surface that I'm on. And then there's tension force that is preventing me from falling down. That's acting on me by the rope that's pulling me up. One more time, can we tell whether or not these forces, the net force is 0? We sure can, because if we remove the arrows from this diagram and put them end to end, you can see that you end up right back at the same spot, which means that the net force is 0, which makes sense because I'm not moving. So if you missed any of the notes, you can either go back and listen to the presentation again, or get the notes that you missed from a classmate, and you can always listen to this presentation again because it will be posted on the class website under Forces. Thanks for listening.